Okay, so it's now my pleasure to introduce our last speaker of the day, Professor Sanfeng Wu from Princeton. Today, he's going to be talking about unconventional quantum criticality in monolayer tungsten ditelluride. Could everyone please help me welcome Professor Wu?
Thank you. Thank you, Christina and everyone. I hope you enjoy your stay. So I will be talking about our journey in exploring this material, very simple material of monolayer tungsten ditelluride. So I will have to explain this title or why it's like we call it unconventional, but hopefully at the end you can you can get understanding of what this exactly means. And I will also give some introduction for the background. So I think the very most important introduction is phase transition, how we understand phase transition in general, right? So this Gensmin-Landau theory is the way that we understand continuous phase transition, including superconducting transitions, right? So we understood the order parameter for a phase to be like superconductor to be developed, or the magnet. The way we understand it is from, for example, this diagram here, which is the free energy versus its order parameter. And for example, above transition temperature, above Tc, you have this parabola where the phase is represented by this dot here. There's no really order parameter 0, right? So it's kind of disordered or it's not ordered phase. And then with increasing, tuning the parameter or decreasing the temperature, for example, then we arrive in a superconducting state or the order magnet. There we have finite order parameter. And this type of phase transition is important. One important thing is that it breaks spontaneous break symmetry, and is how Landau characterized phases and phase transitions. The order parameter vanishes right at the critical point. Okay, so this is how we conventionally understand phase transition and superconducting transitions. I'll talk about unconventional, right? So this is one conventional. So what else that we understand? For example, superconducting transitions. There's another one that is, I think is also established, which is Kostelos-Solis transition. Right? This is the way we understand two-dimensional superconducting transition, where instead of that you have order parameter, in superconducting case, the pairing strings disappear or vanishes at the transition. What happened is a topological transition, right? In the ordered phase, in a superconducting phase, now you expect to have this proliferation of vortices and anti-vortices. Right? This is, for example, in the ordered spin system in the two-dimensional, you can have these vortices and anti-vortices. In the superconducting two-dimensional superconducting phase, you can have this because of vortex, right? So when you, for example, when you increase the temperature for the 2D superconductors, then we expect vortex and anti-vortex really, they emerge and quickly, and then they destroy the superconducting state. This is how we understand is a different type of continuous phase transition. I assume we all know this. So this is a phase transition driven by this generations of topological defects. And in this case, in the BKT transition, is driven by thermal fluctuation. For example, you increase the temperature, you dump energy to the system. So this is a 2D superconducting transition induced by temperature. We generally understand that this type 2, so we have vortexes. Okay, so those I also consider as something we understood. What's interesting now is to think about, in 2D, it's good. We want to talk about these generations of vortexes. So what about quantum phase transition in 2D? More specific, what about superconducting transition? Quantum transition for superconductors in 2D, meaning that I'm not going to tune the temperature. I'm going to tune a parameter, for example, magnetic fields or density. Now we know can have electron density tuned superconducting transition. This is superconducting phase transition is of course very important in the history of condensed matter and has been studied for decades. However, I would say we still do not understand it, right? So one of the perhaps very important data set is like this, is a superconducting transition in two-dimensional thin film, from the superconducting state to an insulating state. So the 2D superconductor to the insulating transition. And this is induced by reduced thickness of the bismuth film, and also many, many other measurements for different materials. The data is not every time the same. So it's not universal, right? There's, for example, in this case, there are residual conductance. And all these reports, there's many, many of them. So the superconducting transition, quantum transition, not tuned by temperature, can be tuned by the thickness of the material, distorters, magnetic fields. We kind of agree vortex are important in these situations, but what happens is not really known, meaning that there's not a accept yet theory to describe them. I will mention that. So all these experimental observations also influenced by the belief that there's no 2D metal, right? So it's Anderson localization. So the two-dimensional states, metallic, do you really have a metallic state? In the old days, right, this is an important concept. So a lot of experimental studies, actually, if you look at data nowadays, there is a metallic state. But when they write the paper decades ago, they say it's superconductor to insulate the transition. So some inconsistency if you revisit data published decades ago. This is what has been really systematically examined in this paper. It was published in 2019, where they look at all these superconducting transitions induced by distorted magnetic fields and thickness, for example. So they really look at many of the experiments, and these are both experimentalists and Capitonic and theorists, Kevels and Spivak, who really work on this topic. So I'm just giving you what they introduction here and their conclusion. So there are a lot of history and progress involved in this research, especially in the case where the metallic state, they call it anomalous metal, around the superconducting transition. They really find that, I'm just going to read it. They will be argued that the robustness and ubiquitous nature of this observed phenomena are difficult to reconcile with any existing theoretical treatment. So it's a very outstanding problem. And they speculate some theories, but not really the final theory yet. Okay. So what I'm going to say in this talk is that I'm going to give an example of monolayer tungsten ditelluride, where we can tune the transition of superconducting state to an insulating state by gate electrodes. So I would claim that the situation is even more interesting. Even maybe you have not just what has been described in this review paper, but there may be something very fundamental has been missing, and we're very excited about these findings. I want to walk you through of this finding. Okay, so this is a material that we have been worked on for several years now. So I think I studied this material, the monolayer. So Bob Kawa grew this material here at Princeton. It's a big ball crystal, allow us to really think about exfoliating the monolayers. So I worked on creating monolayer of this material since 2015-ish from there, and we really see a lot of interesting phenomena in this material. So this is a 2D crystal which has a lattice structure like this. And the red bar is tungsten, the blue is telluride. It's a TMD, transition metal dichalcogenide. But it's very different from other TMD that you have, I think you have heard a lot, because this is distinct from all the other ones, like the stable ones that most of people are studying, which is the hexagonal structure, those 2D semiconductors. This is not a unit cell with a hexagonal structure, it's a unit cell with rectangle. Okay, so this, you see, this is a one unit cell. So that's the key difference. So it's very different from graphene, very different from semiconductor TMDs. So there's a side view. This is still the TMD of telluride, telluride, tungsten telluride, right? But they arranged in a very different way. As a result, the unit cell is rectangle, so the beryllium zone is also rectangle. Okay, this is the key difference, but there are also a lot of similarities between this material and the semiconductor TMD, also graphene, the hexagonal ones, in terms of their band structure and barrier curvature physics. What I mean is that the following, you will see what's the key difference between graphene, or you can think of as gapped graphene, which is similar to the TMD material, semiconductor TMD. So I'm going to compare what's similar and different between the two materials, right? Monolayer tungsten ditelluride versus graphene. Okay, this I think is highlights what's really interesting and what's different from the other materials. So in graphene, we know this beryllium zone is hexagonal and it have K and a minus K point. So interesting physics happen at this 2 point, high symmetry point. And what's most interesting, of course, have Dirac comb. And then you can engineer the Dirac comb, right? This is a linear band, linear comb really exists up to 1 eV, something like that. We also have 2 Dirac comb in monolayer tungsten ditelluride. It does not happen at a high symmetry point like K or minus K. It happens at this Q and minus Q. Okay, this is not high symmetry point. And in the middle of the beryllium zone. That's one key difference. And the Dirac comb is not really the perfect linear line. Instead, here we have a tilted cone. Okay, something like this. So your cone is tilted and very highly asymmetry between electron and holes, not like graphene is very symmetric. And this is why this material was predicted as type 2 wire semimetal. Monolayer tungsten ditelluride, one of the first material predicted as the type 2 wire semimetal. Okay, but not monolayer, they predict in the bulk. Okay, so the list of difference of them is like, from the point of Dirac comb view, you already see the 2 tilted Dirac comb. And then in graphene, there's no spin-orbit coupling, negligible. Here's very strong spin-orbit coupling because of TMD, right? It's a TMD material. And in graphene, also negligible extonic pairing potential. Here's very strong. Again, it's a TMD material. Graphene is gapless. We know it. This material, because of this strong SOC and external binding energy, it become gapped. So it's the insulator. Its intrinsic form in the monolayer case. And graphene is very isotropic. You already see from the lattice this material, the tungsten ditelluride is very anisotropic. Right? So this is almost, you can think of it as a zigzag chain, or you can say this is a rectangle has a aspect ratio between A and B direction. So I already mentioned about electron hole asymmetry. There's also a very strong correlations in this material. You will see. So if you look at the what's the Fermi surface at the charge neutrality, which means you just exfoliate, and then you look at how many electron holes you have. It looks like this electron. So without gap it before in a single particle picture before you see like the insulating states, you have electron pocket on the 2 sides of the whole pocket in this rectangle. Okay, so experimentally we do see semimetal in Fuller and bulk. That's very much confirmed, and it's actually one of the first things to be confirmed when this was initially synthesized in the bulk case. It's called compensated semimetal, which means you have exactly equal number of electron and holes. Okay, what's really surprising is that the monolayer, if you exfoliate down to monolayer, is actually insulated. This is the very first surprise that we had because we saw this in semimetal. And if you look at band structure calculations and property of the bulk is all semimetal. And then we think we're going to exfoliate, get a monolayer, we have semimetal. We'll study property of semimetals. But at the end, we find an insulator. So this is one of the very big surprise in the beginning. So it was also predict, in this specific type of structure, because they have, like barrier curvature hotspot. If you have gapped state, then you have topological insulator, quantum spin Hall effect. It was predicted as the quantum spin Hall insulator a similar time when we start working on the experiment, and we spent several years to really confirm that it is indeed quantum spin Hall insulators, and the bulk is insulating charge. The theory initially do not predict that the gap exists, but experimentally says gapped, and then very happy ending. You have a topology from theory node and insulating gap in the middle. So we checked all this property of the quantum spin Hall. It does exist. Okay, so but that's not enough. As I mentioned, it's very strong extonic pairing. So later on, we realize this extonic insulating state also is very important to the phase. I'm giving you a review of the back because this is a pairing phase. I'm going to start the phase transition out of this, charge neutral topological extonic insular phase. But this is our current understanding of it. So the material in reality looks like this on the optical microscope. And this is the high resolution scanning transmission electron microscope where the white spot is tungsten. What I'm saying here is that showing you this is really exactly what I plot. So the real material, single layer in reality is what I was showing you in the PowerPoint. Okay. And if we look at the resistance map as a function of top gate and bottom gate in a typical two-dimensional device, we have two gates to control the density. I think you're already very familiar from previous talk, right? So the charging royalty lines here is very strong insulators. So what happened is that this band structure, because of both SOC, strong spin optical coupling, and external pairing, you get at the end the insulating state here. Okay. So yeah.
We don't get this cone at the high symmetry point, because generally we have all the maxima and minima of valence band and conduction band at the high symmetry points. But is there any particular reason why we are not having these on the high symmetry points?
Yeah, what happened is this cone is not in the high symmetry. I don't think it's a symmetry reason that you have to go there in this case. Yeah, it's a semi-metal actually. It's not really have a gap, so you have a special point there. So what happens is this the band structure it does not violate anything if it happened here. Yeah. Okay. So there's what's really amazing in this material is that I think there's a yeah.
Why is the fuel air system semi-metallic and the monolayer insulated?
Why is it?
Fuel air system semi-metallic.
This is also an indication of interaction is important. So if a multi-layer, the screening will be stronger, so it's a weaker interaction, right? So it's only in the monolayer and bilayer. Bilayer is much weaker insulating states, right? So this is, when you have in the bulk, it's very strong screening. And in the monolayer, now you have, external binding energy is enhanced. So that's part of the reason why it's interaction driven. Yeah. Okay, cool. So there are a number of puzzles in this material that we really do not understand. There's two outstanding ones, I think. One is the lambda quantization, which in this material, I mentioned this is insulating material, right? It's topological and externally insulated. It's very rare. How many material are quantum spin Hall insulated? How many of them are externally insulated? You really put them together, then you find a number of interesting phenomena. One thing is you see that you try to dope a lot of electron holes, especially in the Hall side, you do not really get a metallic state. There's a wide range of doping. There you have insulating states in the Hall side. And what's accompanied with this extonic pair is that you see, as you already see, I think from Nong's talk, that this kind of apply electric field, it can have a flatness of the band. In this case, the extonic pairing interaction drive actually very different electron hole states. On the Hall side, what we know is that if we measure the density of state here is very huge. So on the Hall side, it's really strongly correlated. You have very high peak in the density of state. So what we experimentally observed is a wide range of Hall doping that you have insulators. And in this insulators, there's a very puzzling quantum oscillation developed in the insulating states. We now observed both in the resistance measurements and also thermal power, where you apply a temperature gradient and measure the voltage drop. Both resistance and thermal power show observe the consistent oscillations. This is very hard to explain without thinking this is intrinsic to the insulator. So the both observations really give very little room to interpret using some extrinsic way. Now this is why I think it's very puzzling, because quantum oscillations is a property of metal. So this links to I think a very outstanding problem in condensed matter, which is can insulator have a quantum characteristic of metals? And here I think this is deserve a lot more study to really figure out what's the situation here. I'm not going to talk about this puzzle. What I'm going to talk about another puzzle, which is also very puzzling and interesting, and I'll walk you through, which is related to dope to the electron side, okay, not Hall side. Dope to Hall side, we get wide range of insulating state. Dope to electron side, you quickly get a metallic state, and that metallic state becomes superconductor. This is one of the very big surprise when we first saw this in 2017. It's actually before the twist magic angle graphene. So we really have, at that time, found an interesting situation where you can gate tune an insulating state with small voltage to a superconducting state, where the critical density of the electrons is about 5 or 6 different devices, slightly different values, but it's around 10 to the 12 per centimeter square. Okay, so you can completely kill an insulator, which is a very interesting insulator, as I already mentioned, to a superconducting state. Yeah.
Incrementally between like an excitonic insulator and just charge ordering or something like that.
Yeah, that's why in the previous we have a paper on this to really figure out how to identify the external insulator. So far, for all external insulators, there's no like conclusive proof. You say like superconductor, you observe 1, 2, 3, confirm it. But what we do is we really rule out, for example, a simple band structure insulators by doing density tuned tunneling spectrum. There's also Hall effect. There's a whole paper there. So there's a bunch of experimental evidence and also theory to allow us to say that we really do not know any else except external insulator. So it's a very strong case of external insulator. Not compared to many bulk external insulator candidate, there's problem of structural transition and real external insulator. Here we don't have that problem because we can do the gate-tuned tunneling measurements. Yeah, so the case is very strong. Okay, so what's really interesting is this transition. Okay, so first what's surprising, then you can ask a lot of question about the superconductor. Like, is this BCS type superconductor or something topological because you come from a topological state? Right, those are outstanding questions. But what I want to address is how this phase transition happened in this material, okay, in this talk. So, so the key is to study this quantum criticality tuned by gate. This is a very clean, right, way of tuning the transition, not tuning by adding disorders or reduce the thickness and so on. So the key here is to probe the quantum phase transition by looking at fluctuations, quantum fluctuation, and I will explain that. Okay. So the way to probe, you will see later, you will see soon why this experiment will help. The way to probe quantum fluctuations in this case is to measure the Nernst effect, which is a thermoelectric effect by applying a temperature gradient, and you observe voltage drop in the transverse direction. Okay, so the key here is, it's not typical quasi-particle or electron driven Nernst effect. It's a vortex-driven Nernst effect. That's what our target. And the reason you can see that is because of this. So this is first applied by Huang An to investigate cuprate, and there was a lot of exciting developments in that area. So the key idea here is that assume you have a superconductor here, and then you apply a temperature gradient. Okay, let's say you have some magnetic field, so you have a vortex. And then if you have a temperature gradient, so it's a superconductor is a condensate, which is very quiet, right? It doesn't carry entropy. But if you have a vortex there, in the core of the vortex, there's normal electrons which carry entropy. So what happens if you have a temperature gradient, then this normal electron will diffuse, will follow the temperature gradient, right? You'll move because of the presence of the entropy and temperature gradient. Right? So this temperature gradient will drive this vortex to this way. Now think about in a superconductor, and you have vortex, so which means the phase will change by 2 pi if you go around the vortex, right? So in a superconductor vortex, the phase will change by 2 pi. Now, if you move your vortex, like this vortex move, what does that mean? The phase here near the electrodes will change as function of time because of a moving vortex, right? Which means if I consider the phase difference between these two contact, then they will have a phase, you already see it, phase here, very far away, it's 0, the other direction, you have 2 pi. So you will see a change of the phase between the two electrodes by 2 pi, like this. Yeah.
Does vortex follow the thermal gradient?
So the vortex, so in a superconducting condensate, they don't have entropy. It's condensate. It's quantum. And then you have a vortex means have normal electrons there. Any normal electron have entropy, right? And then you have temperature gradient will follow that. Because that's you drive the entropy and want to go to lower temperature. So when you have this vortex move, then you will pick up a phase difference as function of time like this, right? which means in the Josephson relation, remember, phase difference in time, d phi over dt will give you a voltage. Okay, so this is very different from the normal Nernst effect, which you drive electrons and the electron will bend like this, right? That's not what we're talking about. We're talking about a vortex motion in the superconductor, and then you introduce a phase difference, a phase time-dependent phase, d phi over dt, that gives you a voltage. This is because of Josephson relation. Okay, so you can now, without applying any electrical current, just by applying a temperature gradient, that's this whole device is aimed to do for 2D material. That's why it looks like quite a little bit more complicated. But the point is to apply a heat here through this heater, and then you generate temperature gradients along the 2D plane, and then you drive this material in the superconducting state. If you have vortex, and the vortex will move along this temperature gradient, and that signal will be the motion of the vortex. If vortex doesn't move, you do not see any signal. The motion of the vortex will be picked up by the electrode in the transverse direction. Right? So it looks like Nernst effect, but it's not the typical Nernst effect. It's the vortex Nernst effect. Do you agree on this? Right. Good. So then what we are going to do is measure this Nernst effect as function of the property of the superconductor. And this experiment was done by Tianchen Song. He's now in University of Wisconsin Madison. He did his work as a postdoc here. So this is a real device that he made. It's basically something like this. And of course, we have electrodes here, so we can check transport. Right? So this is the typical transport we observe as function of the density. So we dope electrons to the material and the temperature. Right? So you tune the external insulating state to a superconducting state. The question now is to ask what the Nernst effect, what the motion of vortex looks like in this material. Okay, and the motion of the vortex is the fluctuation of the superconducting state. Right. So when do you see a vortex? For example, I can drive. I can apply a magnetic field in the perpendicular direction so that I can tune the superconducting state to the normal metal state. Okay, so the magnetic field induced transition. So in resistance, if we don't, this is two curves are two separate experiments. The blue curve is the resistance measurements. What I'm plotting is the resistance of the flake, Rxx, as function of the magnetic field applied in the vertical direction. Okay, so what you see is the transition from zero resistance state to a finite resistance state. Then how to understand this transition? In 2D case is that you have applied the magnetic field, they create vortex, and the vortex is there so that they will generate, again, similar way to voltage. And that's what you have resistance. In this case, it's because you apply current. If you measure resistance, you might apply current. The current will drive the vortex motion. And then that's why you have a finite resistance, because you have finite current with finite voltage. Okay, so now if I turn off the current, only look at the voltage developed by applying a temperature gradient. There's no electrical charge current. It's only temperature gradient. Now you see the red curve. The red curve is you see the Nernst signal, which reverses its sign when you change the B field, first of all. And second, there's no signal here in the very small field because there's either no vortex or the vortex is not moving. So you have very good zero resistance superconducting state. Okay, and then you have a peak here, which signifies that now you have mobile vortex. And then you apply temperature gradient, this vortex move, so that it will have a Nernst voltage signal, and then come back to zero, because after that, you do not have the vortex anymore. You go to normal states, right? It's normal electrons, do not have superconducting condensate. So the fact that go back to zero tells us that we do not worry about the Nernst effect coming from electrons or holes. Because if they are there, they should be finite here. It will be like a linear line like this, because it's Nernst transverse. So we do not see any of that. So it's not there, it's negligible. Compared to the Nernst signal arises from vortex, those quasi-particle signal is very small, so we don't worry about it in all my presentations. Okay. And then you warm up the temperature, you see the Nernst signal this quickly, it smoothly disappears, just like superconducting tradition. So what those data are saying that we do in this device, we do observe Nernst effects arising from vortex. Okay, so the key Okay, this is some background. This was, as I mentioned, was applied to cuprates by Huan, where they really find a lot of interesting phenomena, especially above TC. It's one of the early day evidence of the pseudo gap above TC. There are superconducting condensate, the vortex liquid. Okay, so by now this vortex vortex nurse signal has been observed in many superconductors, not just cuprates, in many thin film as well. And it has been established as a very sensitive probe to observe fluctuations. So the vortex motion is the fluctuation of the superconducting condensate. So before I go to more details of the observation that so far I'm just calibrating what we have done. It's an experimental calibration. So we're now ready to see what happened at the phase transition. I'd like to mention this paragraph that I read from Phil Anderson. He's trying to think about cuprates for, as you know, many years. And in his last work on cuprates in 2016 was on arXiv. I was looking around what he was really doing, and then find this paragraph. I'm going to read it. You can think of this as the most important background. With this, you can understand what I mean when I give you the new data. Okay. So as I mentioned, Huan observed this vortex liquid states in the cuprates above TC, right? So, and he was thinking about this problem, and he said he tried to understand as BKT theory, because this is the KT theory, cost-solid transition, because cuprate is two-dimensional. Okay, and then this will give you proliferations of vortex pairs, right? That's how when you warm up the temperature, where you see what happened in cuprates. So, and then he described all these things. At the end, he said, therefore, if you rise the temperature, you see a considerable range of temperature above TC, where we assume that superfluid continues to be well represented, because it's not like a superconducting gap all closed. And then as the liquid of vortex, so you still have vortex, you still have a superconducting condensate and a lot of vortex there, right? This vortex liquid, this is called on-vortex liquid, it terminates in temperature at higher transition whose nature I don't know. Okay, he's saying that I can understand what's going on in the beginning following the KT theory, but then, right, this is something like this. So the fluctuation signal, or the vortex signal, as a function of temperature in cuprate, he's trying to describe as this. So in the superconducting state, you don't have the signal, and then you have KT type of transition, allow you to have a proliferation of vortex and anti-vortex. And there's a wide range of temperature that you have this liquid state of vortex. So they are mobile. Okay, that's why you lost the resistance. And then at very high temperature, then what's going on? He don't know. That means he knows how vortex was generated, but then how they disappear. At the end, they have to disappear, right? So this gives you one thing is that we do expect in 2D case a broad range of vortex liquid. It's kind of asymmetric pattern. You have rapid rise of this fluctuations, and they have a broad range of vortex liquid, and then what's going on we don't know. Okay. So I will remember this. I will talk about the data that is in contrast to this. Okay, so what we are interested in, not the temperature-driven fluctuations, we're interested in quantum fluctuations. So I'm going to talk about how we drive the phase transition in lowest possible temperature in monolayer tungsten ditelluride through gate voltage. Okay, so so this is the same device previously I showed. I quickly go for experimentalists. I quickly go through how we did it. So it's very important to keep the temperature very low, because I talk about quantum transition. I don't want the effect of temperature goes in. So I want to only see quantum fluctuations. So the key idea is to apply the temperature gradient through a gate. Here is a graphite narrow stripe that can be used both as a gate to tune density of the flake, and also is a very, because as millikelvin, this is the only good thermal conductor. So it will provide you a thermal gradient that's very reliable and robust. Okay. So this is a device, and then what I'm showing here, if we apply this voltage, the nurse measurements using these 3 different gate electrodes. One is on silicon oxide, the other one on boron nitride, the other one on graphite. You see very different appearance, right? The one on this graphite gives you very good signals. If you slide it away from it, but it's, on boron nitride, see a little bit, but then if away on silicon, it's very weak. So at the end, with this geometry, you can also bring the heater closer to the flake like this. Then we are able to generate a temperature gradient of 5 millikelvin per micrometers with only a power of 50 picowatts. It's very small. So we still keep temperature very low. The electron temperature sample is still on the order of 50 millikelvin. It's very low. So what I'm saying is that we achieved to apply a tiny temperature gradient while we can generate a good amount of temperature gradient, allow us to measure the Nernst effect at millikelvin. Okay, now let's do the experiment. We're going to watch how this phase quantum fluctuation change as function of gate voltage, and want to see what happened at this transition temperature, transition density, critical density. Okay, so the first thing we're gonna do is to look at the previous data I showed you was look at the very high densities here. Okay, so what we're gonna do is to magnetic field dependent of the Nernst as function of density exactly here. So the vertical line is the magnetic field. Right? So that's why you see a different color, red and the blue. The red is the fluctuation when you have vortex in positive field. Right? This is vortex liquid I was talking about. And the blue is just opposite, is symmetric, opposite field. And then you reduce the density of electrons, you see how this change. Okay, there's a lot of things going on here. And what's most important, there are regimes of I call 1, 2, 3. And I will talk about them. And I can do a contrast between this map, which is the Nernst effect, which is a fluctuation, versus resistance map. Okay, this resistance shows is both the same thing, magnetic field and the density. What we see is zero resistance here, where you also have zero Nernst effect, which means there's no vortex or vortex not moving. But if you look at the resistance map, you don't have much things going on here. Right? It's not changing. It's just flat. But you see a lot of fluctuations in this region 1. I tell you, actually, Nernst is much better than resistance in telling what's the quantum fluctuations in the system. Okay. And the other things you see that what I'm plotting here is, this is where resistance do not change. But if you go to this region 2 is where the critical point happening, right? So you have very strong fluctuation here, fluctuation getting weaker and weaker here, very strong here. Okay. So one important note is that this fluctuation that you see here, they all come from quantum fluctuations. Because if I warm up, all the signal disappear. This is maximized, signal is maximized as the lowest possible temperature. And temperature here, I keep the 50 millikelvin, the lowest possible. So everything has quantum fluctuations. I have already shown you 2 types of quantum phase transition in this map, single map. One is go through magnetic field, you go up. There's a magnetic field induced quantum phase transition. Right? The other one is go to charge neutrality, reducing the electron density. So that's also quantum transition without involving a temperature. Okay. So we are interested in this transition. But the magnetic field induced transition is also very useful in obtaining the understanding. Okay. So then I'm going to talk about regime 1, which you see this actually goes up rapidly. So something that goes really up very rapidly on this boundary. Right? So we understand this boundary because this is where the zero resistance is. What's absent in the resistance measurement is something like here, something like this, right? So which is highlighted in this map, where now the resistance, the magnetic fields apply up to 500 millitesla. It's very big. So you see that's a boundary we call BCN, which is the white curve rapidly goes up when you go lower density, approaching the critical point. So there's something rapidly increase. This is information not seen in the resistance. So what is this? So if you look at this data, what I'm saying is that you're starting from a superconducting state, and then you increase the magnetic field, which means you bring more and more vortex into the system. And then this BCN is really when the vortex signal disappear, right? So that's when you have too many vortex, and then all the electrons become normal. So this is really the up critical field. So the resistance is not really a good probe to up critical field, but the Nernst is. So that's what you see. So you see the upcritical fields where electron become normal, increase rapidly with decreasing density. And the upcritical field in a superconductor, in this case, it can be interpreted as a pairing strength, which means the pairing becomes stronger. Okay, the Kubo pair becomes stronger and stronger when you go to density that's close to critical. This is against the Landau-Ginzburg, because remember in the beginning, Landau-Ginzburg theory tells you the pairing strength or the order parameter go down to 0. This is not the case. This is not the Landau-Ginzburg picture. The pairing strength actually goes up very rapidly. So first of all, that's very on Euro already, yeah. Where we see here, we start disappear. There is very weak. Here. So here is not really getting the insulating regime. It's still kind of metallic, but it is insulating, but it's not really in the charge neutrality, where you don't see the NERS. You see a lot of noise. It's not NERS because it does not change sign. Right. No, this is a raw data. This is raw data. So that's why it's perfect NERS here. And then you know there's a gap where there's no signal, I'm going to talk about. And then you run into the regime where the measurement is not reliable. Yeah, that's a very good point. So I'm saying that pairing induced really rapidly increase, which is against the Landau-Ginzburg picture. So it's not Landau-Ginzburg anymore. And that's one thing. The other thing I'm going to highlight is to the critical point. So here we see we use the magnetic field to detect signal. The key point is to really, what's the fluctuation looks like if I do not apply any magnetic field, only reduce the density of electrons. Right? So that's the transition that I'm interested in. I want to see how transition happen if you reduce the density of electrons, and that's what happened here. So we apply a little bit of fields, only a few milli-Tesla, because we still need to see the signal, right? So what really happens here is that you have no signal, no fluctuation in the superconducting states. And then you keep reducing density as no fluctuations because you still have a good superconducting state until suddenly at one point here, then the fluctuation really develops. So you have a proliferation of vortex and anti-vortex very strongly, right? The problem suddenly next moment it disappeared. Now you think about what Anderson have told us, right? What Phil Anderson was saying that you change the parameter like temperature, you generate the vortex, and vortex should still stay there, right? And for a while, and then it disappear. This is not the case. It rapidly increased, too sudden it disappeared. Okay, that's the biggest puzzle. If you now, this is just a cross check of what we are observing. We're observing a quantum transition that's at the end of the KT. What do I mean by that? Just look at this diagram, which is I choose one cut here, very small magnetic field. Basically, I want 0 magnetic field, but I need a small field to see the learned signal. And this is the fluctuation pattern as a function of temperature and density. So this is a KT transition. This is a superconductor. If you go warm up temperature, see KT transition, right? So everything we detect here is quantum because you see it's the end of the KT transition at the going to the limit of the 0 temperature. So there you see the strongest fluctuation. So everything we see here is quantum fluctuation. And that's the quantum critical point. At this point, this fluctuation really rapidly develops and to give you a very large signal. How large? So this Nernst coefficient, due to the vortex Nernst effect we measured, is one of the largest values among the records of all material. And in other materials, they have semi-metals will have electron holes. You need a very high mobility to see large Nernst coefficient. More importantly, those large values cannot happen from the conventional quasi-particle picture. They do not happen at 0 temperature because the 0 temperature everything freezes, right? So this is the example that only happened at 0 temperature of huge Nernst coefficient. So this is a really large fluctuation here. It indicates the highly mobile vortex and anti-vortex develops here. The real puzzle is really what happened here. So they rapidly disappear. Okay, I call it the sudden death. So the real puzzle is the sudden death of the fluctuation, which and why we do not have the broad range of the vortex. And what do I mean by sudden death? Okay, first of all, you see there's no signal here at what I call 1' regime. So these two are maps that I already showed you. The only difference is that this map has a higher power of the temperature heater, so which means a higher temperature gradient. And you see this 1' happened at this density of about 20 at 60 millitesla, so about 20, 60 millimeters somewhere here. You have a huge signal when you have higher temperature gradient. Zero signal at here. So we do not have signal in 1' only because the temperature gradient is small. So our instrumental sensitivity is not enough to resolve it, right? So that's not sudden death. We still have fluctuation here. We do not see it in the experiment. That's it, right? The sudden death is the regime 3. Now you see the regime 3. The same map, different power temperature gradient. Regime 3, like this is a 5. Here's a 5. There's no signal here and no signal here at all. It's very sharp transition up to very high magnetic field. So regime 3 really has no fluctuations, no learned signals, no matter at all, magnetic field and all heat powers, all temperature. It's just no fluctuations. So it's really a sudden death of the fluctuations, and that's a problem. Okay, so this is also the contrast between regime 3 and regime 1'. So another, I'll just quickly go through the data here. So another interesting data is look at what happened in the regime 3 in the resistance. In this case, it's a metallic-like state. Right? So what I'm plotting here is the Nernst fluctuation signal as function of the gate and the B field is normalized by B. So you really see the fluctuation is a property of 0B, even though I need some B field to measure it, but it's a property of 0B. And also the resistance measurements correspondingly. Here you see the fluctuation corresponding to this regime, but suddenly everything disappeared in this regime. Okay, and this normal metallic regimes has a resistance of 1 kilo ohm-ish. It should, in principle, support fluctuation, but it didn't in this case. So what happens is now you have a superconductor in this case, and then you reduce the number of electrons. You still have a superconductor until you reach a critical point. You have boost of many vortex and anti-vortex, but the next moment they'll disappear, right? So that's very surprising. We also reproduce this very reproducible observations in other devices. It's a different device already, but you see the same. Everything's the same. So let me now mention going back to the conventional wisdom of superconducting fluctuations. I will present both this conventional and unconventional. So at the end, I'll tell you that we discover 2 types of quantum critical point. One is unconventional. One is more or less okay to understand. Okay, so in this non-Gainsbourg picture, we should have this order parameter disappear at the critical point, but it's not. It's opposite to what we have. It's totally different. We have increasing of pairing strengths. And even though in this conventional picture, we usually expect fluctuation pattern looks like this, in the disorder side, right, you have longer tail of fluctuation because on the order side, the developer order phase really to suppress the fluctuation. So that's what you expect, right? And in the KT transition, you even have perhaps broad liquids of the vortex signal. So you do have very broad transition on the normal side. This is also experimentally observed, for example, in cuprates. You see there's a magnetic field induced transition. So this is how the shape. On the normal side, you have a fluctuation pattern really penetrate into the normal state. There's asymmetry pattern, right? So deeper, larger fluctuation on the normal side, not on the superconducting side. And we observe here it's very different. It's too sharp transition here. So the transition, you see, suddenly disappeared here is sharper than even the superconducting side. If you look at here, the superconducting side is it's also sharp because it's ordered, but it's even more sharper on the normal side. Okay, that's something we really don't understand. But now you can think about why a superconducting state suppress fluctuation, because it developed some orders. So maybe there are some order developed on this side too. That order on this normal state suppress the fluctuation. So we kind of running into the situation that we need another order on the side here. We have a question mark. So really, am I talking about the transition from an order state to another order state? It's continued transition. in a superconducting transition. And we also checked it got to be a continuous transition because it's not first order. We do not see any hysteresis. If you ramp up and back, left and right of the density, you never see a hysteresis. Also, it's a KT, the end of the KT transition, right? So it's a continuous of goes to end. So experimentally, we cannot find any evidence of first order. It's also, if you look at resistance function of gate, this transition, the blue is temperature driven, red is density driven. So it goes through transition by doing the temperature transition induced by temperature and the gate. They're really similar. So it's a continuous transition that connect two order state. If you run into that question, then there's a very interesting. This is really, I'm not sure, but if you get to the point, then this will develop. You will find, what kind of continuous transition can connect two order states. Then you get this deconfined quantum critical point. It's a very exotic theory describing unconventional quantum transitions. It was initially developed in these spin models where you have, this is Neal order on the square lattice, where you have another, valence bond order, and then the theory try to match, try to put these two orders together with a continuous transition. And of course, this is not what our case is because this on both sides are insulated. It's only describing a spin system. What's really interesting is in this paper later on, they apply this idea to a quantum spin Hall insulator versus superconducting transition. So there is some very interesting theory saying that if we have a special kind of quantum critical point that can connect quantum spin Hall insulator and a superconductor. So this really very much looks like what we have, but we don't know what's really is this the case or not. So a concrete theory for tungsten ditelluride is still needed, and I'm presenting a puzzle, and this is if you are interested in theory behind it, maybe it will be helpful. So something to think about it. How much time I have? 20 minutes. Okay, great. Yeah. So I'm going to. It's very long. You have questions? You can ask. More than 1 hour. So I'm going to quickly list, what I think is really interesting. If we want to think about theory, because I believe there are theory behind here. So this, so-called deconfined quantum critical point is a continuous transition, which I think experimentally we have something like that. And then you separate two order phase that cannot be described by a non-log Ginsburg theory, where in this case, in this proposal that I was mentioning, what happened is that you have a superconducting state, and then you have, if you reduce, for example, some parameters, density or electric field or interaction, the key is to have vortex and anti-vortex, the topological defects developed in one of the order states, and then they condensate, the quickly develops at this point, and then they condensate to a new state, new order state. This very much looks like what I was trying to describe, right? So in this specific case, what they want is a ordered quantum spin Hall state. There you have also a topological defect if you go the other side, right? The topological defect is charged 2e skyrmion in this quantum spin Hall state. And then just like vortex, they condensate at this point to get a superconductor. So experimentally, we are probing the vortex and anti-vortex. So this half, we have experiments. And then we have a puzzle of why the sudden death. I think if somehow we can find evidence of this charge 2e skyrmion, then the story will be much more convincing, right? So, but what happened really here is an open question still. The challenge is that this so-called deconfined quantum critical point is still very theoretical at this moment, and there's a metallic state there. So in the pure theory there, they don't want a metallic state because they don't know how to deal with any metallic state. There are too many gapless excitations, and they need this quantum spin Hall insulator, not a trivial band insulator, where you don't have this spontaneous order developed, right? Which is actually very relevant in our case because as I mentioned to you in the beginning, we have extonic insulator. The quantum spin Hall insulator we have is not the single particle quantum spin Hall. It's extonic, there might be extonic order and so on. So there are indeed something encouraging here to think about it. And of course, I think one of the keys to detect the charge 2 is fermion if we want to be more concrete. So I don't know about this theory, but at least the experiment I show you here, I think what I want to say that to study different kinds of quantum critical point, there's a way, which is to probe quantum fluctuations. In the superconductor, we know how to do it now. For other orders, it's more difficult. Okay. I used the last 10 minutes to quickly go through some new findings that we have. One thing is that, as I mentioned to you, that if you look at TC, you think, oh, TC goes down like this, right, in the device 1 here. So, but if you look at Nernst, the fluctuation, I already told you, in the same device, you actually see something rapidly increase, which is the order parameter, right, the pairing potential of the superconducting state. Now, if this is the case, then why we see this in the transport, right? It turns out that's only because of disorder, because what happened on so-called TC is only TBKT, which is very sensitive to disorder, because that's the transition induced by vortex, sorry, right? So using the exact same fabrication procedure, we have another device now, looks like this, where even the transport resistance, we have TC now goes up. Those two, there's no, we are not intentionally doing anything. It's just a different device that we fabricate, which means we have here better mobility, a better quality device. That's it. Okay, so now we see a transition in the resistance now even goes up. So there's no question about it. It's confirmed. Okay, it's conclusive that the pairing strength goes up. Okay, what's even more interesting in this device is that now you apply some magnetic field. Because the pairing strength here is weaker, so you can expect that we actually kill superconductor here first, right? So then you're going to have a dome, which is exactly what we see. You apply some magnetic field, 75 millitesla, then we see a dome where superconducting state now is the middle, and high density you don't have superconductor. What's amazing about this map is now you see two quantum critical point, two quantum phase transition induced by density. One is go this lower density from same superconducting state. The other one, I increase the density, go to higher, right? What's the difference? If I told you this guy is special, then is this also special? Or, right, so there are two quantum critical point absorbed in single device now, and then we want to contrast them, okay? So this is how we measure the data more comprehensively. So by the same resistance data in the top row, their resistance as function of density and temperature, okay? You see how we apply magnetic field, this is zero, very small field to high field. You see the transition happen at the critical point. Sorry, the superconductivity develops around the critical point. You see this is very different behavior. As I said, there's a dome, but one side of the dome, which is high density side of the dome, is very sensitive to magnetic field, right? Zero field like this, and small field like go this way. But the low density side of the dome has no dependence on magnetic fields. Do you see this, right? This is very strange. The critical point fixed here, it doesn't change. This is the unconventional critical point that I was talking about. And then the other critical point moved dramatically with the magnetic field, like this, right? This doesn't change. Okay, so there's something, it tells you it's two kinds. It's very different. Their response to fields is completely different. Right? And then you measure the Nernst effect, okay? So you see the fluctuation. You see the very sharp unchanged, the one that doesn't move with field is still fixed here. Very sharply, you have a sharp point where, it doesn't make sense. Both sides quickly disappear. It's a sharp peak. But the other phase transition, quantum phase transition, at high density is very broad. Okay, the second one, now I show you, it's kind of okay. Now you're thinking about what Phil Anderson was talking about. This guy, that's fine. You generate vortex, you have a broad range of vortex in the parameter. Here is density, and then they disappear. Still, we don't know how they disappeared. There's still a question mark, right? But that's the next problem. The biggest problem is this one. You really generate the vortex and then suddenly disappeared the signal. Okay, so there are two quantum critical point we discovered. One is follow what Phil Anderson has described. The unconventional low density one does not, and that's the very strange one, and it's an interesting one. So there are more data I'm trying to show. One of the things that's very weird is this superconducting state really develops out of nowhere. So what I mean nowhere is you look at the conductance of the density or the Hall effect of the density. Hall effect is you can extract the density of the electrons, right? Both. So conductance, which means a linear line, which means follow NE mu, right? So boring NE mu formula, and in the middle of the NE mu, you develop superconductor. Why is that? Right? So which means you cannot assign this development of superconductivity at the critical point to something like high density of state. I don't have that, right? To a Van Hove singularity, I don't have that. So it's certainly not the BCS type of phenomena. It's interaction induced. Some in the middle of somewhere, we do not see anything in the band structure. It's interesting, and then you develop this critical point, and where superconductor shows up. Okay, so we don't think it's a BCS mechanism, and is the superconductivity developed at the quantum critical point? There's two ways to think about. So this is my kind of summary slide. So how to think about relation between superconductivity and the quantum critical point? Okay, there's one phase diagram that we're familiar with. We're talking about this. So it's if you tune a superconductor through, for example, doping here, and then you kill it, then you have a quantum critical point. That quantum critical point should be very sensitive, for example, to magnetic field, right? Because this is where the gap, the pairing is the weakest. So if you apply field, you suppress the pairing. So it should be movable, my second one, right? So that's the conventional phase diagram, one conventional. The other one is in some of the unconventional superconduction, like heavy fermions, and also maybe cuprate. Some people argued that there's a quantum critical point existing there. It's hidden in the dome, and the fluctuation at the quantum critical point promotes superconductor, right? So there's a promotion of superconductivity around a quantum critical point. There you have dome, and this is the second type of phase diagram. People you already see it in describe the cuprate and also heavy fermion. What I'm talking about, this is a new type, very different type. This tungsten ditelleride has a phase diagram where I have something like here, I have a quantum critical point, really promote the superconductivity here, but only on one side, not on the other side. That's the strange part. And then you have a dome. That dome on the other side is more like conventional like this, right? So this is very different than the other one. This happened right at the edge. This is consistent if you want to use the deconfined quantum critical point, it's consistent with that picture, but we need more concrete understanding connection to that. Okay, this is just telling you that the two quantum phase transitions. And that's my journey. So I have open questions, but thank you. Mostly by Princeton, Yanyu, and also many other groups, members that helped. And Crystal was grown by Leslie and Bob Carver. We have a lot of discussion with Fong and Japanese group for boron nitride. So thank you.
Yeah. Is there any sign of inversion symmetry breaking there?
There we don't have like experimental sign. We only have indirect observations. But in theory, they're arguing there might be charge density wave, spin density wave, or even some spin spiral. That proposal there. Yeah, we need to detect it. Any other? Yeah.
One other one. So you saw when you had two devices, one of them had the DC down. So there, how is the magnetic field dependence in the device one? Because I think you only saw the device two.
You mean in device one, how this, how this also quickly suppressed. But the problem this guy is good is because when I suppress this one, I also have very clear dome here. This guy is very consistent, the same thing. If you not look carefully, you would. So what happened is this doesn't change, but this drops. But then they don't have this like very clear dome like because this is really high. You see, so what happened is that it's the same thing, and this doesn't change, but you have everything like fluctuating. It's not as clear as this. I want this to be zero, right? The other thing is this doesn't go to zero, so you just have some broad fluctuation pattern. Yeah.
But there is
consistent, so this doesn't change. Yeah. Yeah.
Can you say what will happen if you're making the device much more narrow? So maybe, like compared to the size of the vortices, maybe you can enhance know the critical field? Or?
Yeah, that's
Interesting question. We're also thinking about. So maybe we have a broad, wider device and the junction in the middle, and they can control how the vortex goes. There's something we're thinking about, but not really have a device on that yet, because this is very difficult to measure. When you have a wider, so we always have an electrode to connect it, right? So this is air sensitive material, so not many things that we can do. Not like graphene, I can etch to any shape. This one we still have some limitation experimentally, but we do think about what happened with narrow junction, and can you control the single vortex motion, things like that. Yeah, but that's an interesting suggestion. Yeah.
Have you studied the dependence of the superconductivity with the displacement field?
There's no displacement field that we see here. We observe, we try to see it, but we don't see any. So it's mostly on the electron side. It's independent. Yeah. Good. Yeah.
About a question about the sudden bias of this. Yeah. So, in my practice, is it that the sudden bias is real because it's like a long-lived distribution?
Is that range? Range.
But I don't know whether there is a very strong correlation. Why this is real? Because the only common example is that when we increase the temperature, there is a long-lived distribution for the fraction percent. Is there any other example that we should expect a long-lived distribution on the disorder side?
Yeah.
So of course, there's the things experimentally we always observe longer tail fluctuations in the disorder side, right? Because there is nothing to really kill the superconducting fluctuations. So you have longer experimentally. Now, whether it's theoretically you have to have that, that's not the case, right? So we will now give an example that this actually can suddenly disappear, right? So in general, that's a previous understanding that you should have fluctuations longer tail on larger fluctuations on the normal state. Yeah, so certainly this experiment certainly tells you there's two types, right? So then we have to figure out what's going on here. It also tells you, I didn't show the data, but it's actually interesting. I don't have the data here, but if you, there in superconducting transitions, people talk about you have the duality picture where you have the h/2e square, which is h/4e square resistance. That's what you typically expect. You may have a transition, right? The resistivity should be h/4e square, like 6 kilo ohm. The data here prove that that's at least not complete, because if you look at, so there's two transition here, right? As function, the two transition here, as function of the density, the resistance goes like this. Resistance changes to resistance goes like this. Then we have transition one's here, the other one's here. Yeah, certainly, if one follows the h/4e square, the other doesn't. So there's a lot of things going on in the 2D superconducting transition we don't understand. Yeah.
So in this quantum spin Hall phase,
Yeah.
what symmetry is broken to enter this? I think the slide before said something.
Yeah, we don't know. There we do not really probe the symmetry in the quantum spin Hall. Okay, what's needed in theory, let's say, what's needed in this slides, in their theory, is some spin have to point to one direction, so we have skyrmion, right? So it's a broken spin rotation symmetry, which could be what relevant in the experimental because we have the spin pointing to one direction, but that's not proved. We have some evidence, but not proved. Yeah, in this, you need broke some symmetry. Like skyrmion means you have spin aligned. Any other?
Okay, if there's no more questions, let's thank Professor Wu.